people entering into a national park, onto a bridge. In the original article that talked about the tragedy of the commons, it was people having babies, so bringing kids into the world. Okay, those people entering into something, they impose a cost on other people by crowding things up, congestion, but they only bear a small private cost for doing so, in particular because there's no entry fee. There's no gate locking people out. Okay, so that's what we mean by free access. And the idea of the commons goes back to like medieval Europe, where you graze your cattle on the commons, and there was no fee for doing so. Everybody could just go out and use the commons. It's kind of interesting because in the U.S., I think we started off with commons, like, you know, the whole state of Wyoming was essentially like a commons until they decided to start fencing it off and turning land into public or government-owned land. But now we're at a point in the U.S. where the tragedy would start to kick in, where you've got overgrazing if you don't manage the grazing lands properly. Okay, going back into medieval times, you could dump as many cows as people had onto the commons, and you weren't going to eat up all the grass because there just weren't enough cows. Okay, so it's really a question about magnitude and the number of people trying to work their way onto one of these things. So the title, the notion of the tragedy of the commons came from an article, I think this was back in the 60s, by Garrett Hardin in Science. So Science is, you know, one of the leading journals in science in particular. But if you publish an article there, it's a big deal. Okay? Economists, it's kind of tricky because if you work in environmental economics and you publish an article in Science, people in the Nicholas School would be like, that's the best article ever, you know, that should get you tenure, and people in the econ department are like, I've never heard of this. It's kind of an awkward thing if you're in environmental economics, but I'm past the point in my career now where I care, but I'm still trying to, you know, maybe someday crack an article into Science. But Garrett Hardin wrote this article in there about the tragedy of the commons, where he sort of made the phrase stick. And the key sort of argument in there was that the earth is like a commons, like free grazing land, and it was really mostly about kids and congestion costs. So he was arguing that this was sort of in the time when, it may have been in the 70s, you should know this, when there was a lot of discussion about planet, spaceship Earth kind of thing, where we have a limited amount of resources, and if we use them all up, we're going to be out of luck. You know, we're going to talk about natural resources and non-renewable natural resources in late November, and we'll see how even non-renewable natural resources tend to renew and pop up when the price gets high enough to induce people to go out and look for new resources. But in the 70s, there was this notion that we're going to run out of everything. Okay, and in the infinite sense, that's true. We will run out of everything. I mean, it is a finite planet. So the notion was that we needed to restrict the number of people having kids because that would reduce this congestion externality. The congestion externality being that every new kid who is born imposes a cost on everyone else, you know, by virtue of eating up more resources, and that gets to be a bigger and bigger cost the more people there are there to impose the cost on. Okay, so it's sort of an increasing cost as you get more and more people. Now, I did have one other story that I'm not going to play because we would be here for a really long time just listening to the radio. But if you search NPR environment children, this will come up right away. And this is actually relatively recent, just a year old. And it's basically about what Hardin was saying, but in current context. Okay, so it's about climate change, and you know, people are a source of carbon, and an argument being made by a prominent scientist that we should just have fewer kids or we're never going to meet the targets that we need to meet to prevent catastrophic climate change. Like, he's making the argument that you can't get there just by switching over from coal-fired power plants to solar. Okay, and whether that's true or not is, you know, that's a subject for debate. But the argument, you know, pops back up again and again, coming from this notion of Hardin and the tragedy of the commons. Hardin wasn't writing about climate change in the 70s. That just wasn't a thing. In the 70s, they actually thought it was going to be global cooling, and we were headed for another ice age. Okay, so this advocating for sort of constraining the entry into the free access into our world was what Hardin was about. But since that time, congestion externalities and tragedy of the commons has really started to be more about sort of, in particular in the environmental sense, managing public lands and national parks and recreation sites and things like that. It also plays a role in urban economics. Not specifically about environmental stuff, but you can get into a lot of good questions about congestion in an urban setting. So we're going to talk about it in the context of national parks, which are particularly good for this case for the reason that you just heard them talk about, because written into the constitution of the national parks going way, way back is the notion that they're not allowed to preclude anyone. So you're really not allowed to charge a price that keeps people out, okay? But that when you don't have a price to keep people out, you're going to get too many people there, and we'll see how that diminishes the experience to the point where maybe it's not worth it anymore to have the parks. Okay, but you can think about bridges. That's another good example. Just highways in general. In certain cities, congestion is pretty bad. Yeah. So basically, there's this mandate that we have to keep them open for everyone, and how we're going to manage that. All right. Now here's the graph that is different. It looks different to start with because normally what I've given you up until this point is a graph with marginal things. Marginal benefit from another unit of pollution, the social marginal cost of another unit of pollution on breathers, and things like that. And here we're going to start with the totals, okay? So we got the total utility that everybody who's entering into, in this case, to pick your favorite national park, is receiving from n number of people entering the park. That's the total utility that all of them are getting. Okay, and then the total cost, which we're just going to assume the cost per person of getting into the park is a fixed number. It's just a constant. Okay, and that cost would involve, if there's no entry fee, it would involve the gas and the time and everything else you need to get there. Okay, so the shape of this line, the shape of the total utility line, is where all the story, the entire story about congestion externalities, is wrapped up in that shape. Okay? And it's drawn very specifically to have that shape. Now, the intuition for why it's concave, so it's concave function. And there's features of a concave function that we're going to rely on a lot for the arguments we're going to make. The reason why we draw it as concave is because every individual is going to, when they enter, impose a cost on everybody who's already there, which means the first person who comes in, it's just all pure utility. Right, that person gets, they're the first person to walk into Zion National Park that morning. Nobody's around them. They're enjoying the view. They can walk wherever they want, not wait in line for anything. The next person who comes in is going to bring less total utility to the aggregate because they're going to get the joy of being in the park the same as the first guy, but now they're going to get in the way of the first guy when he tries to go on a hiking trail, right? Now, initially, that's probably not much of a diminution of the total utility because just a few people in the park aren't really going to get in each other's way. But more and more people are going to start to get in each other's way worse and worse. So you get up to a point where the next individual to enter up here is now clogging up hundreds of people's experiences and reducing all of their utility. We hit a point up here where we might max out the total utility, and the next guy might actually make everybody in the park worse off than they were before he entered, right? So not even just the total utility didn't go up by less, it actually went down, okay? Now that person we're going to see in a minute is still getting a utility that's bigger than his cost of entry, so he might still decide to enter the park even though he's dragging the aggregate utility downward, okay? Until we actually get to this point right here, and we'll see in a few minutes why that point is where the last person would come in. Okay? Yeah, question?
So basically, the utility gained by the new person coming in is less than the cost imposed on everybody else?
Yeah, so what we're going to assume is that everybody in the park, this is just for simplicity, we're going to assume everybody in the park divides up the aggregate utility equally. So the first person who comes in doesn't have to divide it with anyone, they get the full benefit. The next person who comes in adds less than the first person did, and then we're going to take that total and divide it by 2. The third person adds even less, and we're going to take that and divide it by 3. So you can see that everybody's utility that they're getting is actually falling as more and more people come in, because every person's increasing it by less, and we're still dividing by n. Okay, yeah?
So then is it better to have the number of people the intersection of the two, or at the maximum difference between the two?
So which one would you think?
Well, I thought it'd be the maximum difference, but...
Yeah, so we're going to get to this point later, but there's going to be a spot in here where the utility in excess of the cost of everybody getting there is maximized, and that would be what the social planner would pick.
But the individual wouldn't see that as a...
The individual has no reason to stop there. We're going to see the individual incentives is to go all the way out to this point where the net utility is actually driven to 0. So people just keep entering until the last person makes it so that nobody is really happy to be there anymore. It's kind of how you enter, right? And if you've been to like Yellowstone in August, that's probably about right. Especially if you're there with kids and you're like trying to see the Old Faithful and like there's just hundreds of people in the way. So, yeah, so we've kind of, that's basically the whole argument. We just kind of talked through it in just a few seconds. So let's put a little bit of meat into it here. Okay, so we were just basically saying that the total utility we're going to divide up by the number of people. That's just for simplicity. It could be different across individuals, and in complicated models you'll make it different. But for simple purposes, we'll just say divide it up. So what that means is, in graphical terms, the slope of that line is the aggregate utility divided by the number of people, right? So I've drawn it there as U of n over n. Total utility is U of n divided by n. The slope of that line there, the yellow line, is the utility per person when that many people have entered, okay? And that's going to be really important because that's the thing that they're going to now, the marginal entrant is going to think, I'm going to get the slope of that line if I come in. How does that compare to my cost of getting to the park? Okay, which is where the total costs come in. So I've already, I drew it into the graph originally here. The cost of entry is just going to be the same for everyone. We'll call it little c. Okay, the cost of visiting the park. So the total cost for everybody who's there, the costs they all incurred to get there, is going to be that cost per person times the number of people. Okay, so the cost per person is the slope, and the number of people is the run, and the slope times the run will give us the height. Okay? So the marginal entrant is going to compare the utility they would get, which is the slope of this line, the line leading from the origin to any point on the aggregate utility curve. They're going to compare that to the cost they're going to incur, which is the slope of the red line. Okay? So you're going to see then that it's going to be worthwhile for them to keep entering, right? As long as that slope is bigger than that slope, which is going to be true as we work our way over until we get to NC. And I've drawn NC. The C here means two different things. That's the cost of entry. And with C, what I'm referring to here is the competitive equilibrium. Okay, so in an open access situation, we talk about the social planner's solution, and then the social planner's equilibrium, and the competitive equilibrium, which is when everybody does what they want to do. Everybody maximizes their own utility. Okay? What we're going to see is the competitive equilibrium is really inefficient. All right? Because it's going to essentially take that net utility difference there that we talked about a few minutes ago, and it's just going to burn it all up with over-entry. Okay? So we're going to see a model that looks actually really similar to this when we talk about elephants and fish and renewable resources later in the semester. Because the model that they use to talk about sort of hitting the right level of effort in harvesting from a renewable resource stock basically has built into it a dynamic congestion externality, where if you get free access, free entry into a fishery, you're going to get too many boats and too many fishermen, given the the sort of biological dynamics and the ability of the fish to reproduce themselves over time. Okay? So we're seeing the model here in the simplest sense, which is people coming into a park, and later we're going to layer that into a model of biodynamics. Yeah.
So in this curve with the fish in the boat example,
Yeah.
What point would we be at when the last fisherman goes in and says, oh, I can't fit? Like, not that there's not enough fish,
Yeah.
but there's just too many.
It's essentially going to get out to this point again. The big difference is going to be that instead of the aggregate utility of everybody entering the park, this is going to be a total revenue function for fishermen versus a total cost, and we have to derive the total revenue function from underlying bioeconomic processes. We're going to have like fish reproduction functions underlying that. Okay. You guys will have to derive those on a problem set. So anyway, so that's all coming down the road after we do the benefit stuff. Okay, so simpler now though. We know, so we're going to get to the competitive equilibrium if everybody just does sort of what they want, which is the world without policy. Everybody would just optimize on their own, doing the best that they can do, which would get us out to NC, which drives everybody's happiness down, net happiness down to 0. All right, so here's where the graph is essentially the same graph you saw before. So sometimes we'll talk about congestion externalities in the previous graph, and sometimes we'll talk about them on a graph that looks like this. So just to see where it came from, if I were to take the slope of the line drawn from the origin to the aggregate utility function at every value of n, it starts high and it gets lower and lower and lower until it intersects with the cost of entry, right? So little c. Essentially, all I've done here is I've plotted the value of the slope of that line, right? And it goes down and down and down and down as more and more people enter until we get to the point where we've hit the competitive equilibrium, where the slope of the line drawn from the origin to the utility function is the same as the slope of the cost function, okay? And that's going to be our competitive equilibrium. So individuals will enter as long as the utility they get is bigger than the cost they incur. And everybody else's utility will be the same as they drag it down. Okay. Okay. So the over-entry part of this is because of the fact that that aggregate utility function has a concave shape, right? So when a person enters, they drag down everybody else's enjoyment, and nobody asks them to pay for it. Okay. If, as you entered, somebody at the park gate said you're about to reduce everybody's utility in Zion National Park by 25 cents, and there's 10,000 people here right now, so 10,000 times 25 cents is 2,500. That's your entry fee. Would you like to come in? The person would probably stop and not come. And you'd work your way back until you get to the social planner point. So what we want to do now is look at what the social planner solution looks like on the graph, figure out where the dead weight loss triangle is. We're going to have another dead weight loss triangle. We always do in these things. And then figure out how you capture it through policy. Okay. And what's nice about this is that you actually get policy in the real world that mimics kind of what they were describing on the radio story at the beginning is something that we can very easily see built into the graphs in just a few minutes here. Okay, so here's where the shape of that function really matters. Okay, this is a feature of concave functions, and you can kind of see it if you just look at the graph for a second. I drew in a red line and a yellow line to make the point. The additional utility that the next person coming in contributes to the aggregate is given by the slope of the aggregate utility line. That should kind of just make sense from like differential calculus, right? The increase in the total is just the derivative at any point. So the first guy coming in has a really, really high derivative because he's only adding his own utility. And then as more and more individuals come in, what they add to the total goes down because they pull everybody down with them when they enter, right? So we get to this point up here where the last guy, that guy is basically not contributing anything, and the next guy is negative utility total aggregate. So what's nice about concave functions is that the line drawn from the origin to any point on a concave function is steeper than the slope of the function at that point. You can kind of see that from the red line and the yellow line. Okay? If you drew it as a convex function, so one that's shaped like this, the opposite would be true. The marginal would always be steeper than the line drawn from the origin, the average slope. Okay? So that's really important because now what we're going to do is draw on the slope of the yellow lines at every value of n onto the graph that we were just working with. Okay? And that's going to be the marginal utility associated with the last entrant. And that's essentially what the social planner is going to think about. The social planner looks at what is the last entrant contributing to the total. The individual, not the social planner, looks at what they're going to get by themselves, not what they're contributing to the aggregate, but what am I going to get, right? And do I enter or not based on my own utility versus the costs. Okay, so here's the graph with both of those lines drawn in. What we've got is the slope of the line drawn from the origin to any point on the aggregate utility function. That was u of n divided by n. And then we've got the slope of the aggregate utility function itself at any point. And at every point along the way, the slope of the function we said was less than the slope of the line drawn from the origin to that point on the line, right? That's the feature of a concave function right there. So the social planner is looking at the marginal utility function and comparing it to the cost and saying it's good for people to enter if what they contribute to the total utility is bigger than what they contribute to the cost. Right? And compare those values. And the social planner would say stop at n star, and that's exactly the point where those two functions have the biggest difference. Okay? Whereas the individual is going to say, I'm going to compare what I'm going to get to the cost of getting there, my own utility to the cost of getting there, and they're going to keep entering out to the competitive equilibrium. Okay? So where's the dead weight loss triangle going to be on this graph? The same principles apply that you've seen to, evaluate dead weight loss triangles before. It just looks a little different. Yeah.
Is it going to be above the C line between n star and n and C?
Yeah. So,
yeah.
In there?
C line.
Is it? What do you guys think? What's the rationale for finding the dead weight loss? I go to the part where I'd like to be. Shinjin, you're gonna.
So it's the triangle between n star to nc, but it's what the load is C.
Okay, yeah. So we've got it kind of colored in here, and it's funny looking, right? Because it actually goes negative, which we haven't seen that before. That's fine though. You can. The interpretation when it gets negative, you kind of have to flip things around in your mind, but it's still dead weight loss. Okay. What we have here is the cost of the additional person coming in over and above what their contribution is to the utility of the aggregate, and that's going to be a positive. Well, I mean, the cost exceeds what they contribute to the total utility all the way up to NC by the amount of that triangle right there. Okay. So up here, right, this line up here doesn't have any sort of welfare interpretation. This is just the line that individuals think about. The social planner thinks about contribution to the total and total utility and contribution to total cost. Okay, so when the social planner does it, they're going to look at the marginal utility and stop at n star, and then the difference between those two things is going to give us the dead weight loss triangle. Okay? So this is when we have free entry into Yellowstone or Yosemite or any of these really crowded parks, you could quantify the monetary cost of over-entry, the amount of sort of surplus and utility that people could be getting if we could put a gate on the front and lock people out, which goes, we could, I mean, they have a gate, but they're not allowed to force people out with money according to the constitution of the national parks. And you could quantify just how much worse off people are if you knew the height of line C and if you knew the marginal utility. Right? So what would make this triangle get big intuitively? Yeah?
If, like, the difference in slope between the marginal and
Yeah.
steeper,
Yeah.
so if it was steeper, then it would
So
go up.
if these lines opened up a lot, right? if there's a big gap between the two. What does it mean for there to be a big gap between the two if you were to go back to the total utility function? Like mathematically, what does that kind of describe, or not mathematically, just graphically, what would that imply? Or think about it differently, when would the two lines be the same and the dead weight loss would go away?
She wants to be the same when it has that intersection.
Sorry, I'm asking, like, when would these two lines collapse on top of each other? And then, yeah, then the social planner would be the same as the competitive equilibrium. Yeah.
When like each person that enters the park, their marginal utility is the same as like the total utility.
Yeah, and what would the total utility function look like if that was true?
Also, I think it would
Be a straight line.
Yeah.
Yeah. So the thing that's making these two things be different is the concavity of the function. So that as more and more people come in, the next person contributes even less and less and less because they're really getting in each other's way. So if I was just going to say you're now the manager of this national park, what would be something you could do to sort of make the total utility function get straighter? And they do this, like, they do versions of what I'm thinking of at Arcadia, and they do it at, some at Yellowstone, although not enough. They do it more at Yosemite. They do it, as we saw at Zion all the time. Right, so if it's like, an idea? No? So what's the source of, has anybody ever been to the Smokies or Yellowstone? No? You're from Tennessee. How
I
good are the
know.
Smokies?
I
You have to,
went when I
like,
was
drive
little.
through there to get here.
Yeah, I mean, yeah, but it's not actually like
Yeah,
going
sure.
to a park.
So the Smokies are famous for there's actually like no entry point. It's just a highway that runs through. And it's the park that most people go to without getting out of their car. So they drive through it and it's pretty and then they just drive out the other end. Which means that most of the people who are in there are actually in their car and the road backs up and it takes like 2 hours to go half a mile to the middle of the park because everybody's stopping. Right. So the thing that oftentimes kills the parks in terms of congestion is vehicles, right? So what they've done at, for instance, at Acadia up in Maine, I know this one, we were up there 2 summers ago, you're not, well, you can bring your car to the various stopping points in this big loop that goes through the park, but you have to pay like $150 to get like the right to go park in any of those spots. There's a free set of shuttle buses where you park in the main lot, kind of out in the front, and the shuttle buses will drop you at any of the points for free. And they're actually good shuttle buses, and they run like every 2 minutes, and they have a ton of them, right? So that's their way of saying, we're gonna take the thing that causes the congestion, which is all the cars, and basically get rid of it. We're gonna straighten this thing out. Now the proper number of people will enter. Now we can't do that by closing the gates because we're not supposed to keep people out based on their ability to pay, but it's not really keeping you out to say you can't bring you have to ride a shuttle bus. And if you're really rich and it's worth it to you to be able to get out of your own car at the stopping point and go up the hiking trail, you can pay us $150 and you can do it. Right? So it's like a graded service and you get more rights to do things if you pay more, but you're essentially not taking away people's ability to see the whole park, and you're collapsing those two lines to be the same. Yeah.
Why not just ban the vehicles in the first? Why not just make everyone go on the shuttle bus?
I mean, they could do that. I think that created a lot of unhappiness amongst people, and they complained that you're taking away our rights as citizens to drive our big cars into the park and do what we want, right? So, and also it's probably for a more nefarious reason. It's probably a good moneymaker because you can really crank the price up if these people have a high willingness to pay. And in general, people when they drive are really like if I were to drive my car from here to Yellowstone, I would probably pay $150 to be able to drive it into the park and park wherever I wanted because I spent God knows how many thousands of dollars getting there in the first place. An extra $150 seems like not much, right? So there's a lot of that sort of thing built into it, where their willingness to pay for things goes way up when they're on long trips, things like that. So, but yeah, you can be very egalitarian about it, not let anybody bring a car in at all. And I think at Yosemite, it's a lot harder to bring a car to a lot of the points in the middle. It's all about buses taking you places. Whereas the Smokies, it's the complete opposite. There are no buses, and the traffic is really bad. Okay. All right. So that's kind of going to be the end point of the discussion. We kind of jumped to it there a little bit. What I want to do now is talk about how you'd recover that dead weight loss through various kinds of approaches, right? Whenever we have dead weight loss, we want to see like what can we do to pick it back up. So this is what it would look like if we just shut the gate, which the National Park Service is not allowed to do. But in other contexts, you could think it's fine to just, preclude entry beyond a certain point. So you just draw a line right there and say, when you get to N star, no more people can come in, okay? So actually in Yellowstone, they do this, but they do it for a very specific kind of entry. There's a big snowmobiling community in Yellowstone. It's in the winter. It's not when most people go there to look at geysers, so it's not really congesting the park for that reason, but it creates a lot of pollution. And they get too many snowmobilers, and they'll argue that it actually does create a congestion cost, right? Nowhere on this graph are we really talking about like social costs. Here, the external costs are coming in the shape of the downward sloping line, not in an SMC curve, okay? So in Yellowstone with snowmobiling, they actually do have an SMC curve because they create a lot of air pollution. But aside from that, the congestion part is a problem. So what they do is they say there's only going to be a certain number of licenses to bring your snowmobile in. They auction the licenses off to registered guides, where I guess they do lotteries and auctions, combinations of the two. And then the guides can go out and sell the rights to enter the park with their guide service for market price. Okay, so that's very much not a sort of like anybody can enter sort of a story, right? But it's hard to think of a way to get rid of the externality, the congestion externality with snowmobiles, other than to just sort of cap the number that are coming in. So that kind of played out a few years ago. They developed this new strategy for auctioning off licenses and having lotteries. Another big community of, especially I think it's in Idaho, the entrance to the park that's up in the northwest corner is where you go if you want to find a snowmobile guide. Okay, so that's what just a simple band or a cap on the number of people would look like. Let's go back to the original graph and say, like, where does this dead weight loss triangle come in? So this is me. This is the first time I've really tried to draw anything with this new app, so it's a little bit quirky looking. I'm still trying to get the hang of it. But before, I had two dots labeled on the graph with the downward sloping lines. The red dot was the competitive equilibrium, and if you go back and look, the yellow dot was the social planner's equilibrium, and this is where they fall on the totals graph, okay? The totals graph has the point where the slope of the aggregate utility function, which is the marginal utility, was the same as the slope of the cost function, right? That's where marginal utility equals C. So that's, we finally labeled now the point that you brought up like 5 minutes in here. And the point is that the amount of surplus that people are getting at that particular level of N, if we were to go to NC, if we were to go to the competitive level of entry, competitive amount of entry, we would wipe out that whole surplus. Wiping out the surplus is essentially the dead weight loss of not stopping at N star. Okay? So the height of that dotted line right there, from the cost up to the aggregate utility function, the height there is actually equal to the size of the dead weight loss triangle drawn on the marginal graphs. Okay? So there's some integral calculus built into this because the area here is essentially integrating back from that point to that point along the two marginal lines, the marginal cost and the marginal utility, right? So if you integrate back, you're going to get the total difference between the two lines, and that's going to add up to be the size of the dead weight loss triangle that you would have integrated up over. Okay? So there's two places you can find the size of the dead weight loss. One would be getting the triangle, the other would be getting the difference between this point and that point, which I didn't label, but it's that point down there. Make sense? Okay? And the other way to think about it would be if you stopped people at N star instead of going to NC, you would recoup that dead weight loss triangle. You're used to thinking about that. And if I were to stop people here at N star instead of going to NC, this would be the total utility, net utility everybody would get instead of 0. So that's maybe an easier way to think about it if you don't like the integral calculus sort of approach to thinking about it. Okay? Yeah?
So just to clarify, the numerical value of that line is equal to the
Area of the triangle, yeah. So that's what I was trying to convey here with my arrow and my triangle that I drew in. That triangle there was from the previous graph, and it is has an area equal to the height of that brace. Yeah.
Then at the ends, not the red point,
Yeah.
what would be the dead weight loss if there's no difference?
Well, so at that point, the dead weight loss is the fact that we took what we could have gotten in maximum utility and we've evaporated it by basically whittling it all away by letting more and more people come in and drag down everybody else's utility. So net utility here is 0. Here it's maximized, and the difference between maximum and 0 is the area of the dead weight loss triangle. Okay. Yeah. I always find it a little surprising, I think because we don't deal with integrals very much, but that you can actually kind of get that same area, that same value off of the total graph, and it has like another interpretation. Always kind of blows my mind a little bit. So we don't usually look at the total graphs. Okay. Yeah, so there's the net utility. I probably should have put that before the description of how it was equal to the dead weight loss. But that's the maximum value of the net utility that we could end up getting. Okay. So the one way of solving this that we've kind of already talked about, a couple of the solutions, but just imposing a limit, and with the snowmobiling, they use lotteries and they use auctions. You can do first come, first served, where you just let people line up, and then the restriction is really one based on the value of people's time, right? So you have the people who can afford to wait in line will be the people who end up doing so, and the people who can't will just be the ones who can't get in. Whereas if you make them pay, it'll just be who's richer. Okay. The alternative, sort of the obvious alternative, would be to impose some sort of a fee. So in national parks, this is kind of not allowed so much, but in other congestible resources like bridges, right, you pay a toll all the time, and that's fine. We don't have sort of the same notion built in that everybody should have the right to cross the bridge without paying for it. But here's how that works in a graphical sense. The toll on the bridge would basically just raise the cost of entry. Okay? So before we had the cost, that people were comparing to their private benefit and entering the bridge up to NC and creating a lot of congestion and bringing a big dead weight loss triangle. The social planner would like to only have N-star people on the bridge and recoup that whole dead weight loss triangle. So one way to fix it would be to take the cost of entry and just raise it so that the private choice, the choice that individuals would make on their own, is actually to stop at N-star. Okay? So I take the price of entry and crank it up. Now the individual is going to compare the utility that they're going to get to the cost of entry and work their way up to that point right there. Okay? So you can think about this in the context of toll roads pretty well, right? I mean, if you were to take a toll road, it might be less congested, and you weigh it in your mind, am I willing to pay whatever the $6 it's going to cost me to take that toll road, and I'm going to get to go really fast, or do I just want to take the main highway and save the $6, right? So you're actually going to make that decision not to go on the toll road when it's more expensive sometimes, unless it's really valuable to you to do so, and you'll stop up there. So why does that actually fix the problem? Well, I mean, on the one hand, we get back to N-star, so we've gotten the individual to do the thing the social planner wants, but where does the net surplus actually go, right? So what's nice about tolls is, from a government point of view, is they take the net surplus at the socially optimal point and they capture it all as government revenue. Okay? And the way to see that is if I were to take the toll that I just had on the graph over there, which I've labeled as F, okay, the fee, I guess, to enter the bridge is F. And if I were to put it on this graph over here, right, what that's going to do is take the total cost function, little c times the number of people who entered, and it's going to crank it up to be little c plus f times the number of people who entered. So the slope got bigger by the amount f. Okay? We have a lot of geometry in this lecture. So if you have the difference in those two slopes is f, and I multiply that by n star, the difference then in the height of those two lines is going to be n star times f. Right? The triangle is going to spread out at a rate of f. So n star times f is going to be what we're going to capture in terms of revenue, but graphically speaking, it's also the difference between the aggregate utility and the cost of entry without the fee, which earlier we said was the net surplus, right? Which was also the deadweight loss triangle. So if you impose the fee, the government is going to capture the deadweight loss triangle for themselves. Okay? So in the end, really, the drivers in this case are kind of indifferent between a really crowded bridge and one where they're paying a lot to get on it, right? But this is efficient in that we're not taking all of that net surplus and just burning it through people's unhappiness and pounding on their steering wheel and just being unhappy. Now they're generally happy except for the fact that they paid a lot of money, but the government got all that money and they can use it to build schools with or whatever, right? So it's not wasting the surplus, it's using it now for something productive. They could use it in a double dividend story and reduce a distortionary tax with it, okay? So that's why it's efficient, even though if I were to ask you in this case, are drivers better off? The answer is really kind of no, right? In both cases, they're getting net utility of 0, right? But here it's because the utility is all going somewhere productive. Okay, so that's not allowed in the context of a national park, sort of, except for the fact that in Acadia, you can pay a high fee to drive in your SUV and take it to the back road parks and not take the bus. Okay, so the last bit here, just we've kind of already discussed it, is this notion that if you can straighten out the concave function, you can basically get rid of the congestion externality. Okay, so one way to straighten it out would be to make it so that people are not imposing costs on each other, right? And how do you do that? Well, you get better infrastructure so that people are not getting caught up at pinch points and bottlenecks and creating headaches. This probably applies to highways, not just to national parks. Then you end up with sort of less of the actual congestion, less externality imposed on everybody else when you decide to enter because things are flowing more freely. Okay, so in the national parks, that's the shuttle buses, but it's having roads without potholes in highway situations, or good off ramps that people aren't getting stuck on, right? Or ways to sort of take accidents and pull them off onto the side so you don't have people backed up for hours and hours. All of these things would basically straighten out the UN curve. Okay? All right. So so that's congestion externalities in a nutshell. I can go back and I can sort of answer some questions about them. There'll be some problem set questions. The problem set on this stuff will come in a few more weeks. We'll come back and talk about these things a little bit in the problem set. But I'm also prepared to answer any questions about the midterm. We have like 20 more minutes. This is sort of a short-ish lecture. But I don't really want to start climate change today for 10 minutes or so. We'll save that for Monday. So first, any questions about these sorts of graphs? Yeah.
Just one quick one. When we're talking, if you go back to the deadweight loss slide,
yeah.
When we're talking about kind of deadweight loss between, the other side, I meant the further one. Yeah, that one. If you're if that red dot, let's just say for whatever reason that red dot was a little bit more to the left of the utility curve, like let's just say it wasn't at the intersection, let's say we were operating a little bit more,
Okay.
somewhere there. would the dead weight loss then be the difference in the height of that big one and the small one?
Yeah.
Okay, just.
Yeah, you'd have to come up with a story why people would
Yeah, just
stop
whatever
there.
reason though. which
But,
is,
yeah, because, I mean, according to the model, they would enter as long as their net utility from entering is positive,
Yeah.
which is true all the way up to the intersection point there. Yeah. But other than that, yeah, if it was there, then that would be the net utility at the point where they stopped, and this would be what they could have gotten.
Right.
So the dead weight loss would be the difference between the two.
Got it.
That's right. Okay. All right, so if nobody has questions about this, then you're free to go early today. I'm gonna hang around.